All right. So up first, we have Arjun Prem, whose mentor is Alexander Selke. I believe he is here. Would you like to say a few words
Yes,
to introduce Arjun?
sure. Hello, everyone. It's my great pleasure to introduce you to Arjun Prim. He's a rising senior at Summit Tahoma High School here in San Jose. Arjun has a really strong background in programming languages, especially Python, which comes in very handy, which was very exciting because I've been exploring the possibility to analyze some of my experimental data on lunar samples using a really clever program. So Arjun was tasked to come up with a program to help my research. So before I steal all of Arjun's thunder and what he has done, Arjun, the floor is yours. Please take it away.
Hi, so I'm going to share my presentation. Can everybody here see my screen?
Yes.
Hi everyone, my project is about analyzing lunar sample thermoluminescence with Python, and I worked with my mentor Alex Self to complete it. My goal for this project was to explore the possibility of TL glow curve deconvolution for lunar samples. Why is thermoluminescence TL important? Thermoluminescence can be used to determine the thermal history of a sample, how hot and how long. Since the presence of lunar resources such as water ice depends on temperature and duration, thermoluminescence may help find water deposits needed for sustainable lunar bases, which utilize water for consumption and rocket fuel. What is thermoluminescence? Thermoluminescence is a property of crystalline materials where accumulated energy from ionizing radiation is released as light when heated. The slide shows a diagram that shows the steps involved for TL buildup and loss. Ionizing radiation excites electrons, trapping them in higher energy levels. Heat provides energy for them to fall to their ground state, where some pass through luminescence centers and release light. The emitted light can be plotted against temperature to generate a glow curve. TL can be measured. The slide shows an example of the TL glow curve, where the black solid line is the measured signal light intensity against temperature. The black line is composed of individual peaks, all of which have different electron trap parameters, namely E and S. Each TLP can be described using the following equation, which has all of these parameters. The ones most important to peak position are E and S, and the peak height is governed by the number of electron traps filled and the total number of electron traps, N. How do we determine TL kinetic parameters? One way to determine TL kinetic parameters is experimentally, but it takes a lot of time and samples. Overlapping peaks require different experimental methods, and we can get a unique solution, but there's a large data scatter. Another way to determine the parameters is to use theoretical fitting, otherwise known as curve fitting. It is much faster and doesn't need extra samples, with only one experimental measurement needed. However, it likely generates a non-unique solution. Modern processing power makes TL curve fitting a viable alternative to experimental approaches. While it's common in lunar science, curve fitting is unexplored for lunar samples with complex TL properties. How did I create a program to theoretically determine TL parameters? Since Python is easy to understand and can run on nearly any computer, I programmed in it to make my program open to anyone. Keep it fast, I use clever algorithms. Instead of reinventing the wheel by programming them myself, I use SciPy and C++ implementations of them. As a result, it outperforms the Excel spreadsheet previously used to determine TL parameters written by Kazakis in 2019. For a dataset of similar complexity, my program took a fraction at a time. The program also has more features compared to the spreadsheet, such as additional solvers and the ability to switch between them, a more direct TL modeling approach, E, F, N0, and N values to the peak temperature, intensity, and N values. What tools did I use? On the Python side of the code, I use several libraries to do tasks ranging from processing data to displaying detailed graphs. On the C++ side, I use a C++ implementation of the differential evolution algorithm as an optional alternative to SciPy's slower implementation. How did the code evolve? Over this project, the code got much more complex as I added new features. The code started from a 61-line single-file Jupyter notebook where I familiarized myself with SciPy solvers. While the Jupyter notebook was great for early prototyping, as I could run my code with a single button, its inability to pass command line arguments to my program made it inadequate. This is why I migrated the code to a 118-line single-file Python program so I could begin adding command line features. Between adding command line features, adding new solvers, and splitting the code into multiple files to make it easier to read, the code expanded to 1,079 lines in 14 files and now included a bit of C++ for speed. To use my program, you must store the glow curve and bounds in CSV files as shown. Then you must run the program with the glow curve, bounds, and number of peaks provided as command line arguments, as well as any additional command line arguments of your choice. After a fit is complete, inspect the graph as the first step to check the quality of fit. Ideally, the figure match should be below 5%. Then inspect the output file to check if the parameters are reasonable within our knowledge of TL parameters for lunar samples. The program's output graph is light intensity against temperature. The blue line is the input glow curve. The yellow line is either a user-provided initial guess or an initial guess the program makes to fit the curve. The green line is the final fitted curve and should be as close as possible to the blue line. The shaded areas are the individual peaks making up the. Finally, the figure of merit is a percentage representing how close the fitted curve is to the input curve, where lower values are better. In the output spreadsheet, these are the fitted TL parameters. These are the initial starting parameters. These are the identified peaks and their intensities at the given temperatures. And this is a copy of the input data. To summarize what I did, I made a Python command line program to deconvolve TL glow curves. I tailored it for lunar sample research and designed it for ease of use. I also made it publicly available on GitHub and wrote documentation explaining how to use it. Also, I learned a lot about TL and programming. I learned about TL's uses in lunar science. And I also learned about Python scientific computing libraries such as SciPy and NumPy, which make processing large amounts of data fast and convenient. In this project, I drew from these research papers, many of which were either wholly or partially authored by my mentor. And I'd like to acknowledge the opportunities that have been provided by thanking the N3 program, Ariana and Alex, for the opportunity to participate and learn about STEM by completing a project about their lessons. This program is something I'm very grateful for, and I can only hope it continues to provide others the same opportunities I had. Thank you for your time, and I'd be very happy to answer any questions you may have.
Thank you, Arjun. Let's give a round of applause for his amazing presentation. I could see Dr. Selke smiling throughout your presentation, so he looks very proud of you and all the work that you've done. All right.
That was just great. What a wonderful project.
Thanks all. Thanks, everyone.
it looked like we had a hand up from a fellow intern, Sid. Sid, did you have a question for Arjun?
Yeah, so basically, does the program, or I guess the collection of programs that you made, does it plot basically like the curve that it plots, is that a result of basically, is it designed to plot that data, or is it designed to interpret that data in some way?
It's designed to interpret the data. If you're curious about how that data is obtained, I can show you an experimental diagram of the machine used to do this. So there's a sample, like a moon rock, a lunar sample, and a heater. The sample is heated, and a photomultiplier too, which is a very sensitive light detector, determines the amount of light the sample emits, the number of photons, and it's graphed in this graph. So this is and also the sample is in an inert atmosphere of nitrogen gas. My program does not generate the data, it merely interprets the data.
Okay, that makes sense.
Okay, thanks. Question. That's a nice one. Does anybody else have any other questions?
Why do the glow curves go up and then suddenly fall?
That's a nice question. The flow curve, so I I can't really provide an exact reason, but if you can take a look at this equation, it almost has like, as you can see the vertex point where it peaks, and each of the peaks here is a vertex, a high point, and then it drops past that. I think I don't really know exactly why. Uh, so I can't really answer that question, but it has something to do with this equation.
If I may just jump in, Arjun, you actually gave the right answer, but just one more step. It is that you have these peaks there. At some temperatures there are just no peaks, and that's why it's falling, or they're really low intensities. And at some temperatures you have some peaks present, and then it can go up. So
Okay,
it
yeah,
can
I
vary.
forgot to mention
So
that.
yeah.
The glow curve is made up of individual peaks, and sometimes as you go to higher values, the peaks become smaller or just like disappear, and that's why it becomes smaller. We're running a bit over time, so does anybody have any final questions?
All right.
For now?
I think that's it for now. If you do think of something, you can always put it in the chat and I'll let Arjun know that there's something there for him.
Okay.
Thank you very much.
I'll handle on to the next presenter.